Linear Algebra II, Lecture 19, Old Examinations. In this and in the next lecture, we will go through all the problems which were proposed at the examination on March 13, 2017. Problem 1. Let f1 of x be the polynomial x plus x squared. Let f2 of x be the polynomial 1 plus 2x minus x squared, and let f3 of x be the polynomial 1 minus x squared. A. Prove that f1, f2, and f3 form a basis in the space of all polynomials of degree at most 2. B. Determine the transformation matrices between the standard basis and this basis f in both directions. C. Determine the coordinates of the polynomial g of x, which is equal to 2 plus 2x minus x squared in the basis f. And D. Find a polynomial h of x whose coordinates in the basis f are 1, 2, and 3. Solution. We note that almost all of the parts of this problem can be solved by one computation. It is quite substantial computation, but it is just one computation. And the reason for that is the fact that if we want to determine coordinates of some vector v in some basis b, what we really need to do, we need to solve a non-homogeneous system of linear equations, for which on the left-hand side, if we look at the columns of the matrix of the system, we will see the coordinates of the vectors from our basis B in the standard basis of our vector space. In the particular example of our problem, the standard basis in the space of all polynomials of degree at most 2 consists of the elements 1, x, and x squared. Then, on the right-hand side of the system, the column which we see in the matrix of the system is the coordinates of the vector v in the standard basis. And in order to solve various parts of this problem, we need to determine the coordinates of various vectors in our basis f1, f2, and f3. So what we really need to do, the major part of our problem, is to reduce the following matrix to a row echelon form using Gauss elimination. So we have a big matrix which consists of 3 parts. The leftmost part consists of our vectors f1, f2, and f3, and the columns are the coordinates of these vectors in the standard basis. Then the middle part is the identity matrix, and the identity matrix is the matrix of the coordinates of the elements in the standard basis with respect to the standard basis. And then the rightmost part is the vector of the coordinates of our polynomial g in the standard basis. So let's do this computation. So we write this matrix. So column-wise, this matrix consists of the following columns: 0, 1, 1. So these are the coordinates of f1. Then 1, 2, minus 1. These are the coordinates of f2. Then 1, minus 1, minus 1. These are the coordinates of f3. Then 1, 0, 0. These are the coordinates of 1. Then 0, 1, 0. The coordinates of x. And 0, 0, 1. The coordinates of x squared. And the last column is 2, 2, minus 1. So first, let us rearrange this matrix such that we write row 3 first, then row 1, and then row 2. So we just rearrange the rows of this matrix in order to have 1 here in particular in position 1, 1. Now we can use this 1 in position 1, 1 to eliminate 1 in position 3, 1. So we subtract row 1 from row 3. Rows 1 and 2 remain the same, and row 3 becomes 1 minus 1 is 0, 2 minus minus 1 is 3, minus 1 minus minus 1 is 0, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, 2 minus minus 1 is 3. Okay, so we look at this matrix, and now we can use 1 in position to 2 to eliminate all other elements in the second column. So we add row 2 to row 1, and we subtract 3 times row 2 from row 3. Row 2 remains the same, and row 1 becomes 1 plus 0 is 1, minus 1 plus 1 is 0, minus 1 plus 1 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, minus 1 plus 2 is 1. And row 3 becomes 0 minus 0 is 0, 3 minus 3 is 0, 0 minus 3 is minus 3, 0 minus 3 is minus 3, 1 minus 0 is 1, minus 1 minus 0 is minus 1, 3 minus 6 is minus 3. So now we can take this matrix and divide the third row by minus 3 to make 1 here. So rows 1 and 2 remain the same, and the third row becomes 0, 0, 1, 1, minus 1 third, 1 third, 1. And finally, we can use this one at position 3, 3 to eliminate this one at position 2, 3. So we subtract row 3 from row 2. Rows 1 and 3 remain the same, and row 2 becomes 0, 1, and then 0 here, 0 here. Here we have 1 third, minus 1 third, and 1. So this is the end of our computation. And this is the row echelon form of the original matrix. Let us note that the leading elements in our row echelon form stands in columns 1, 2, and 3. And this means exactly that the polynomials f1, f2, and f3 are linearly independent. So we have 3 linearly independent polynomials in the space of all polynomials of degree at most 2, and we know that that space has dimension 3. It follows that polynomials f1, f2, and f3 form a basis in the vector space of all polynomials of degree at most 2. The transformation matrix from the standard basis to the basis f is the left-hand side of the former big matrix, the original matrix. So it consists of the coordinates of f1, f2, and f3 in the standard basis. So it's a matrix, when we read it column-wise, 0, 1, 1, 1, 2, minus 1, 1, minus 1, minus 1. The transformation matrix from F to the standard basis is the inverse of the transformation matrix from the standard basis to F. And we computed this inverse on the previous slide. So this is the part which is here in the middle, because we took our matrix and the identity and reduced using Gauss elimination our matrix to the identity matrix. What is now here at the place of the original identity matrix is the inverse to our original matrix. Therefore, the transformation matrix from F to the standard basis is the matrix 1, 0, 1, 0, 1 third, minus 1 third, 1, minus 1 third, 1 third. And the coordinates of the vector g in the basis f are 1, 1, 1. So this is exactly the last column in our computation. Finally, we also need to determine which polynomial h has in our basis f coordinates 1, 2, 3. Using the base change formula, the coordinates of h in the standard basis are equal to the transformation matrix from the standard basis to f times the coordinates of h in the basis f. So we take our matrix 0, 1, 1, 1, 2, minus 1, 1, minus 1, minus 1, and multiply it with the vector 1, 2, 3. We get the vector 5, 2, minus 4. Therefore, the polynomial h is the polynomial 5 plus 2x minus 4x squared. And this completes problem 1. Problem 2. Let f be the linear map from R3 to R3, which has the following properties. So f of 1, 1, 0 should be equal to 1, 0, 1. F of 0, 1, 1 should be equal to 1, 0, 1. and f of 1, 0, 1 should be equal to minus 1, 0, minus 1. A. Determine the matrix of f in the standard basis. B. Determine a basis in the image of f. And C. Determine whether f is invertible or not. Solution. Let us denote by v1 the vector 1, 1, 0, by v2 the vector 0, 1, 1, and by v3 the vector 1, 0, 1. Then we can note that in the formulation, our linear map f is defined by its values f of v1, f of v2, and f of v3. For this to define f uniquely, we need that v1, v2, and v3, this should be a basis in our vector space. To check that v1, v2, and v3 form a basis in R3, we need to compute the determinant of the matrix, which we obtain when we write the coordinates of v1, v2, and v3 as columns. So we need to compute the determinant of the matrix 1, 1, 0, 0, 1, 1, 1, 0, 1. We use the definition, so this is equal to 1 times 1 times 1, plus 1 times 1 times 1, plus 0 times 0 times 0, minus 1 times 1 times 0, minus 1 times 1 times 0, minus 1 times 0 times 1. And when we compute, we get 2. 2 is different from 0, which means that V is indeed a basis in R3. And by definition, the matrix of F, if we start from the basis V and end up in the standard basis, will be the matrix 1, 0, 1, 1, 0, 1, minus 1, 0, minus 1. This is because V1 is sent to 1, 0, 1. This is the first column. V2 is sent to 1, 0, 1. And V3 is sent to minus 1, 0, minus 1. We want to determine the matrix of F in the standard basis. For this, we can use the base change formula. So the matrix of F from E to E is equal to the matrix of F from V to E times the transformation matrix from V to E. And so we need to determine the transformation matrix from V to E, which is the inverse of the transformation matrix from E to V, and this is exactly the matrix for which we computed the determinant. So we need to determine the inverse of this matrix. So the computation is, we write this matrix, and then the vertical line, and then the identity matrix, and we reduce this to a row echelon form, which will have identity on the left-hand side. So here we see that we need to eliminate this 1 in position to 1, so we subtract row 1 from row 2. Rows 1 and 3 remain the same, and row 2 becomes 0, 1, minus 1, minus 1, 1, 0. Now we can use 1 in position to 2 to eliminate 1 in position 3, 2. So we subtract row 2 from row 3. Rows 1 and 2 remain the same, and row 3 becomes 0, 0, 2, 1, minus 1, 1. Now we need to make 1 here at position 3, 3, so we divide row 3 by 2. Rows 1 and 2 remain the same, and row 3 becomes 0, 0, 1, 1 half, minus 1 half, 1 half. And finally, we use this 1 in position 3, 3 to eliminate everything else in the third column. So we add row 3 to row 2, and we subtract row 3 from row 1. Row 3 remains the same, while row 1 becomes 1, 0, 0, 1 half, 1 half, minus 1 half, and row 2 becomes 0, 1, 0, minus 1 half, 1 half, 1 half. And so the transformation matrix from V to the standard basis is 1 half of the matrix 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, 1. Great. So now we can compute the matrix of F in the standard basis. So this matrix is equal to the matrix of F between the bases E and V times the transformation matrix from V to E. So it is the matrix 1, 1, minus 1, 0, 0, 0, 1, 1, minus 1 times 1/2 of the matrix 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, 1. And so the answer is that the matrix of F in the standard basis is the matrix 1/2 times minus 1, 3, minus 1, 0, 0, 0, minus 1, 3, minus 1. Note that all columns of this matrix are obviously multiples of each other. So in particular, if you take any non-zero column, this must be a basis in the image of F. And also, since the matrix of F has a zero row, this matrix is not invertible. It definitely has determinant 0. Therefore, the linear operator F is not invertible either. This completes problem 2. Problem 3. Let N be the subspace of E4 spanned by the vectors V1, which is equal to 1, 1, 1, 0, V2, which is equal to 1, 1, 1, minus 1, and V3, which is equal to 2, 2, 2, 2. A. Find an orthonormal basis in the orthogonal complement to N. B. Determine the orthogonal projection of the vector W, which is equal to 1, 3, minus 1, 2, onto N. C. Determine the distance from W to both N and the orthogonal complement to N. Solution. Let us recall that a vector x with coordinates x1, x2, x3, and x4, this is a vector from E4, such a vector belongs to the orthogonal complement to N if and only if it is orthogonal to all vectors which generate N. So which means that x should be orthogonal to V1, V2, and V3. In other words, the scalar product between x and V1 should be 0, the scalar product between x and V2 should be 0, and the scalar product between x and V3 should be 0. This we can write as the following system of linear equations. So this is a homogeneous system of linear equations. So that x is orthogonal to V1 is equivalent to saying that x1 plus x2 plus x3 is equal to 0. That x is orthogonal to V2 means that x1 plus x2 plus x3 minus x4 is 0, and that x is orthogonal to V3 means that 2x1 plus 2x2 plus 2x3 plus 2x4 is equal to 0. So x belongs to the orthogonal complement to N if and only if x is a solution to this homogeneous system of linear equations. Let us solve this system by reducing its matrix to a row echelon form using Gauss elimination. So we write the matrix, which is 1, 1, 1, 0, 1, 1, 1, minus 1, 2, 2, 2, 2. So here we write the vectors which generate our space as rows. So here we can subtract row 1 from row 2, and we can subtract twice row 1 from row 3 to get the matrix 1, 1, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 2. So now we see that rows 2 and 3 are linearly dependent. We delete row 3 and multiply row 2 by minus 1 to get the matrix 1, 1, 1, 0, 0, 0, 0, 1. So this is a row echelon form with leading elements staying in columns 1 and 4. So the leading elements are in columns 1, not 2, 1 and 4. So we can take x2 and x3 as the free variables. And then from the first equation we will get that x1 is equal to minus x2 minus x3. And from the second equation we have x4 is equal to 0. And then x2 is equal to x2 and x3 is equal to x3 are two trivial equations for the free variables. In the vector form, x1, x2, x3, x4 is equal to x2 times the coefficient vector minus 1, 1, 0, 0, plus x3 times the coefficient vector minus 1, 0, 1, 0. And therefore, the vectors u1, which is minus 1, 1, 0, 0, and u2, which is minus 1, 0, 1, 0, they form a basis in the orthogonal complement to n. This is some basis, and we need an orthonormal basis. So we apply the Gram-Schmidt method to get an orthonormal basis from u1 and u2. So the first basis element is just the normed version of u1. We divide u1 by its length. So the length of u1 is the square root of 1 plus 1 plus 0 plus 0. This is the square root of 2. So the first basis vector is equal to 1 divided by the square root of 2 times minus 1, 1, 0, 0. To determine the second basis vector, we first compute an auxiliary vector b2 tilde, which is equal to u2 minus the scalar product between b1 and u2 times b1. So since b1 is u1 divided by the length, we can rewrite it as u2 minus u1 times the scalar product between u2 and u1 divided by the scalar product between u1 and u1. And here is the computation. So u2 is minus 1, 0, 1, 0. u1 is minus 1, 1, 0, 0. The scalar product is 1, and u1 times u1 is 2. So we get minus 1, 0, 1, 0, minus 1 half, minus 1, 1, 0, 0. This gives us the vector minus 1 half, minus 1 half, 1, 0. So to eliminate 2 in the denominator, we consider the vector b2 2 tildes, which is 2 times b2 tilde, and this is a vector minus 1, 2, 0. And now we can take b2 as a normed version of b2 2 tilde. The length of b2 2 tildes is 1 plus 1 plus 4 plus 0, it's 6, so the square root of 6. So we get the vector 1 divided by the square root of 6 times minus 1, 2, 0. So the vectors b1 and b2 form an orthonormal basis in the orthogonal complement to n. So now we can compute the orthogonal projection of w on n. We know that this is equal to w minus the orthogonal projection of w on n orthogonal complement. And this later orthogonal projection is easy to compute because we now have an ONB in an orthogonal complement. So this projection is equal to the scalar product between w and b1 times b1 plus the scalar product between w and b2 times b2. So since b1 is u1 divided by the length and b2 is b2 2 tildes divided by the length, we can rewrite it as u1 times the fraction where the numerator is the scalar product between w and u1 and the denominator is a scalar product between u1 and u1 plus b2 2 tildes times the fraction where the numerator is a scalar product between w and b2 2 tildes and the denominator is the scalar product between b2 2 tildes and itself. So recall that w was 1, 3, minus 1, 2, u1 was minus 1, 1, 0, 0, and b2 2 tildes was minus 1, 2, 0. So we can now plug this into this formula, and we get that the orthogonal projection of w onto the orthogonal complement of n is equal to, so w and u1, so what we get, minus 1 plus 3, it gives us 2. So u1 scalar square is 2, and then the vector u1 plus the scalar product between these two vectors, minus 1, minus 3, minus 2, 0. So this is minus 6. And then b2 2 tildes with itself was 6. We knew that. So times minus 1, 2, 0. So it's just the difference between these two vectors. And we get 0, 2, minus 2, 0. So the orthogonal projection of w on the orthogonal complement to n is equal to 0, 2, minus 2, 0. This means that the orthogonal projection of w onto n is w minus the projection onto the orthogonal complement to n, and so it's equal to 1, 1, 1, 2. Finally, the distance from w to n is the length of the orthogonal projection onto the orthogonal complement. So this is the length of the vector 0, 2, minus 2, 0. This vector has length root of 4 plus 4, which is 8. Also, the distance from W to the orthogonal complement of n is the length of the projection of W onto n. So this means that this is the length of this vector, 1, 1, 1, 2, which is root of 7. And this completes problem 3. Problem 4. Let f be a linear operator from R4 to R4, which has the following matrix in the standard basis. So the matrix is 1, 1, 2, 2, 1, 1, 2, 2, 0, 0, 3, 3, 0, 0, 3, 3. A. Determine whether f is diagonalizable or not. B. If f is diagonalizable, determine a diagonal form and the transformation matrix to the corresponding eigenbasis. C. Determine whether f is invertible or not. Solution. Since the first two columns in our matrix of f in the standard basis coincide, it follows that the image of E1 under f is equal to the image of E2 under f. But this means that f is not injective, and therefore it is not invertible. So this completes the solution to part C. Now we need to determine whether f is diagonalizable or not, and this we always start with computing the characteristic polynomial of f. So we take the matrix of f in the standard basis, subtract x on the main diagonal, and compute the determinant. Here we observe that this is a block upper triangular matrix with 2 times 2 blocks on the diagonal. So this determinant is equal to the determinant of the matrix 1 minus x, 1, 1, 1 minus x, times the determinant of the matrix 3 minus x, 3, 3, 3 minus x. The determinant of the first factor here is 1 minus x squared minus 1 squared, and the determinant of the second factor is 3 minus x squared minus 3 squared. So in both cases we have difference between two squares. So the first one is 1 minus x minus 1 times 1 minus x plus 1, and the second factor is 3 minus x minus 3 times 3 minus x plus 3. If we collect this together, we will get that our characteristic polynomial is equal to x squared times 2 minus x times 6 minus x. So we have three eigenvalues. The eigenvalue 0 with algebraic multiplicity 2, the eigenvalue 2 with algebraic multiplicity 1, and the eigenvalue 6 with algebraic multiplicity 1. So for diagonalizability, we just need to check whether the geometric multiplicity of 0 is 2. This is the only thing we need to conclude that the matrix is diagonalizable. So let's check that. Let us find all eigenvectors for the eigenvalue 0. Such eigenvectors are the solutions to the homogeneous system of linear equations with matrix, our matrix minus the eigenvalue. But the eigenvalue is 0, so we just do nothing. We take the matrix of f in the standard basis. So here rows 1 and 2 are the same, so we delete row 1. Rows 3 and 4 are the same, we delete row 4. And then we will get a matrix, so if we divide here by 3 and then kill this 2, 2 in the first row, we will get the matrix 1, 1, 0, 0, 0, 0, 1, 1. So this has rank 2, so we will have 4 minus 2, two linearly independent solutions. In this case, they are very easy to guess. The vectors 1, minus 1, 0, 0, and 0, 0, 1, minus 1 are obviously solutions to this system. So we denote them by v1 and v2. And this means that the geometric multiplicity of 0 is 2. Therefore, the linear operator f is indeed diagonalizable. Let us compute the other eigenvectors because we need to determine the transformation matrix to the diagonal form. For the eigenvalue 2, the eigenvectors are the solutions to the homogeneous system of linear equations, whose matrix is obtained from our matrix by subtracting 2 on the main diagonal. So we get the matrix minus 1, 1, 2, 2, 1, minus 1, 2, 2, 0, 0, 1, 3, 0, 0, 3, 1. And here, again, it's easy to guess that the vector 1, 1, 0, 0 is a solution to this system. Since the algebraic multiplicity was 1, the geometric multiplicity must be 1, so this is a unique linearly independent solution, which we denote by V3. Next, the eigenvalue 6. The eigenvectors for this eigenvalue are the solutions to the homogeneous system of linear equations, whose matrix is obtained from our matrix by subtracting 6 on the main diagonal. So we get the matrix minus 5, 1, 2, 2, 1, minus 5, 2, 2, 0, 0, minus 3, 3, 0, 0, 3, minus 3. And here one can observe that the sum of elements in each row is 0. Therefore, the vector 1, 1, 1, 1 is a solution to the system. Since we already know that the algebraic multiplicity is 1, this is a unique linearly independent solution. And now we can just write down the answer. The diagonal form of our matrix is a diagonal matrix, where on the diagonal we write the eigenvalues, each with its algebraic multiplicity. So we have the diagonal matrix with 0, 0, 2, and 6 on the main diagonal. And the transformation matrix to the corresponding eigenbases consists of the corresponding eigenvectors. So the first and the second column consists of 1, minus 1, 0, 0, and 0, 0, 1, minus 1. So these are the eigenvectors for the eigenvalues 0, which are in the first and second position on the diagonal in the diagonal form. Then we have the third column is 1, 1, 0, 0. This is the eigenvector for the eigenvalue 2. And the last column is 1, 1, 1, 1. This is an eigenvector for the eigenvalue 6. And this completes problem 4. So here are some additional problems and questions. Question 1. In all instances where solutions to homogeneous systems of linear equations were guessed, solve the corresponding system using the standard algorithm. Question 2. Solve problem 1, replacing f1 by f1 plus f2, and then keeping both f2 and f3. Question 3. How can one see directly from the formulation of problem 2 that f is not invertible? Question 4. How will the solution and the answer to problem 3 be affected if we replace v1 by v1 plus v3? And question 5. How will the solution and the answer to problem 4 be affected if we replace the first row in the matrix of f by the negative of this row? Thank you very much and see you next time.